In this lesson, we will discuss the velocity profile for fully developed turbulent flow in pipes. In a previous video, we applied Newton's second law in the axial direction to a fluid cylinder in a fully developed flow. We found that the shear stress tau is proportional to the radius for both laminar and turbulent flows. For laminar flows, we were able to relate the laminar shear stress to the velocity gradient in the radial direction to derive an exact expression for the velocity profile, which is the shape of a parabola. However, for turbulent flows, there exist eddies of various sizes that add additional shear stress. We can write the total shear stress tau as a sum of the laminar shear stress, tau lam, which we already have an expression for, and the shear stress related to the turbulent behavior of the flow, tau turb, which we do not have an expression for yet. We will need to know if the turbulent shear stress is significant anywhere in the flow, and if it is, we will need an expression for it in order to derive the velocity profile from theory. When discussing shear stress in fully developed turbulent pipe flow, it is useful to think of the flow as consisting of three layers. The layer closest to the wall is called the viscous wall layer. In this layer, velocity gradients are relatively large due to the no-slip boundary condition, and the laminar shear stress term is much larger than the turbulent shear stress term. The thickness of the viscous wall layer will be denoted by delta W. The viscous wall layer is very thin. For example, if water flows through a 3-inch diameter pipe at an average speed of 10 feet per second, the viscous wall layer would only be a couple thousandths of an inch. The thickness of the wall layer is highly exaggerated in the image on the right. In the outer layer, which consists of most of the flow, the velocity gradients are relatively low, and the turbulent shear stress term is much larger than the laminar shear stress term. There is a middle layer, called the overlap layer, in which both the laminar and turbulent shear stresses should be accounted for. This means that the turbulent shear stress is indeed important throughout almost the entire flow. So what is the expression for the turbulent shear stress? It can be shown that this term is related to the unpredictable fluctuations in speed that are characteristic of turbulent flows. Accurate knowledge of tau turb is needed for determining the velocity profile of fully developed turbulent flows from theory, but unfortunately the only useful formulas are empirical. A widely used approximation for the time-averaged, fully developed turbulent velocity profile is a power law. The centerline speed times the quantity, 1 minus the radial distance lowercase r over the pipe radius capital R to the 1/7 power.